Hello everyone, this is a presenter usual and today I will present the paper managed communication and consistency for fast data parallel interactive analytics. Machine learning analytics are an increasingly important cloud workload, and the core of many important machine learning analytics is an expert suggestion model whose parameters are refined by interactively processing a training dataset until converges, and the compilation time and the quantity of the learned model not only depends on the rate at which the refinements are generated, but also the quantity of each refinement. For example, deep learning applications refine their interlinear weight matrices to achieve higher prediction accuracy for classification and rejection problems. Topic models refine the word composition and the weights in each global topic to better summarize a text corpus. Sparse coding or matrix factorization models refine their factor matrices to better denoise or reconstruct the original input matrix. The parameters refinement are performed by algorithms that repeatedly compute updates from mailing data samples and push the model parameters towards an optimal value. When the parameters are close enough to an optimal, the algorithm is stopped and is said to have converged. Therefore, such algorithms are called interactive convergent. There are also some problems in nowadays solutions. The algorithm performance may suffer from staleness, resulting in suboptimal performance, and previous implementations of bounded staleness often bounded communication with the staleness threshold and synchronization barriers, or relied on explicit application control of communication. And while data parallel machine learning applications often employ a loose consistency model when updating shared model parameters to maximize parallelism, the accumulated error may seriously impact the quantity of refinements and thus delay compilation time, a problem that usually gets worse with scale. Although more immediately, propagation of updates reduces the accumulated error. This strategy is limited by cycle network bandwidth. Additionally, the performance of the wide-used stochastic gradient descent algorithm, which is also called SGD algorithm, is sensitive to step size. Simply increasing communication often fails to bring improvement without tuning step size accordingly, and tendentious hand tuning is usually needed to achieve optimal performance. So authors want to improve those solutions, and then they meet some new challenges. First of all, they want their system that satisfies the bounded staleness consistency model, which allows computations to use stale model parameters to reduce synchronizations overheads, but strictly upper bounds the number of missing iterations, restoring formal convergence guarantees, while using local model parameters improves computation throughput. It degrades algorithm throughput due to accumulate parameter errors. There is theoretical and empirical evidence showing that fresher parameters lead to higher algorithm throughput. Then another challenge in applying machine learning algorithms originally designed for sequential setting to distribute system is turning the parameters in the algorithm itself. For example, SGD, which has been applied to a wide range of large-scale data parallel machine learning applications, such as edge click-through rate prediction, deep neural networks, and cooperative filtering, is highly sensitive to the step size that modulates the gradient magnitude. Many external distributed machine learning systems require manual tuning of step size by the users, while some provide tuning mechanism. An effective large-scale machine learning system would need to address those important algorithm challenges. So they print the system Bison, which is designed to achieve maximal network communication efficiently by incorporating knowledge of network bandwidth. Through bandwidth management, Bison fully utilizes but never exceeds a pre-specified amount of network bandwidth when communicating machine learning sub-updates and up-to-date model parameters. Bison also satisfies bounded stateless models requirements and thus inherits its formal convergence guarantees. Moreover, their solution maximize communication efficiency by prioritizing network bandwidth for messages most significant for algorithm processing, which further enhances algorithm throughput for a fixed network bandwidth bucket. They demonstrate the authors demonstrated the effectiveness of managed communication on 3 applications: matrix factorization with SGD, topic modeling with Gibby sampling, and multi-class logistic regression with SGD on and up to 1024 core compute cluster, and their experiments on matrix factorization show orders of magnitude of improvements in the number of iterations needed to achieve convergence compared to the best hand-tuned fixed scheduled step size. Bison PS consists of a client library and parameter server partitions. The former provides the application programming interface for reading, updating model parameters, and the latter stores and maintains the model A. In terms of usage, Bison closely follows other key value stores. Once a machine learning program process is linked against the client's library, adding through in that process may read or update model parameters concurrently. The user runs a Python machine learning program by invoking as many service partitions and the machine learning application compute process as needed across multiple machines. Python's API abstracts consistency management and networking operation always from application and presents a simple key value interface like this table. Get is used to read parameters and inc is used to increment the parameter by some delta. To maintain consistency, the client application signals the end of a unit of work when clock. In order to exploit locality in machine learning applications and thus amortize the overhead of operating on concurrent data structures and the network messaging, Python allows application to statically partition the parameters into bunches called rows. A row is a set of parameters that are usually accessed together. A row can also be the unit of communication between client and the server. Row get is provided to read a row by its key, and the row inc applies a set of delta to multiply elements in a row. Python supports user-defined stored procedures to be executed on each server. Those can be used to alter the default increment behavior of inc and row inc. The Python client library and the server partitions have a consistency manager, which is responsible for enforcing consistency requirements on the local parameter image A, thus ensuring correct machine learning program execution even under worst-case delay. The consistency manager works by blocking client process worker through when reading parameters until the local modem image A has been updated to meet the consistency requirements. Bounded staleness puts constraints on parameters age. Python will block if A is older than the work's current iteration by S or more, where S is the user-defined staleness threshold. A's age is defined as the oldest iteration such that some updates generated within that iteration are missing from A. Now let's talk about BSP. When the staleness threshold is set to 0, bounded staleness consistency reduces to the classical BSP model. The BSP model is the gold standard for correct machine learning program execution. It requires all updates computed in previous iteration to be made visible before the current iteration starts. Now we look at the system architecture of Python. The client library provides access to model parameters A on the server partitions and also caches elements of the model A for faster access, while cooperating with server process in order to maintain consistency guarantees and manage bandwidth. This is done through three components: a parameter cache that catches a partial or complete image of the model A at client in order to server read requests made by compute threads. 2. An updates buffer that buffers updates applied by computer threads when psinc and psrow inc. 3. A group of client communication threads that perform synchronization of the local mode cache and buffer the updates with the service master copies, while the computer threads executes the application algorithm. The parameter cache the parameters cached at the client are hash partitioned among the client communication threads. Each client communication thread needs to access only its own parameter partition when reading the computed updates and applying up-to-date parameters. Values to minimize local contention. The client parameter cache and the update buffer allow concurrent reads and writes from worker threads, and similar to the cache and the buffer, use static data structures and allocate memory for repeatedly accessed parameters to minimize the overhead of maintaining a concurrent hash table. And in order to amortize the runtime cost of concurrency control, we allow the applications to define parameter key ranges we call rows. Parameters in the same row share one lock for access to their parameter caches and one lock for access to their update buffer. When serving read requests from worker threads, and the client parameter cache is searched first, and the read request is sent to the server process only if either the requested parameter is not in the cache or the cached parameter staleness is not within the staleness threshold. The reading compute blocks until the parameter staleness is within the threshold. When writes are invoked, updates are inserted into the update buffer, and optionally, the client's own parameter cache is also updated. Once all compute threads in a client processing have called to signal the end of a unit of work, the client communication threads release buffered model update to service. Bound staleness is ensured by coordination of clients and server partition use the cloud messages. On an individual client, as soon as all updates generated before and in iteration are sent to server partitions, and no more updates before or in that iteration can be generated. The client's communication threads send a client clock message to each other. Indicating all updates generated before and in iteration by this client have been made visible to the server partition. Bison provides fault tolerance by checking pointing and by checking pointing the server model partitions. In the event of failure, the entire system is restarted from the last checkpoint. A valid checkpoint contains the model state strictly right after iteration. The model state includes all model updates generated before and during iteration, and excludes all updates after the TPS clock call by adding worker thread. With bounded status, clients may securely enter new iterations and begin sending updates. Thus, whenever a checkpointing clock event is reached, each server model partition will copy on write protect the checkpoint's parameters value until that checkpoint has been successfully copied externally. As Bison targets offline bench training, restarting the system is not critical. With tens or hundreds of machines, such training tasks typically completed in hours or tens of hours. Considering the MTTF of model hardware, it is not necessary to create many checkpoints, and the probability of restarting is low. In construct, a replication-based fault tolerance mechanism costs 2 times or even more memory on storing the replicates and additionally word bandwidth for cyclism. Bison client library and server partitions feature a communication manager whose purpose is to improve machine learning process per iteration through careful use the network bandwidth in communicating model updates. Communication management is complementary to consistency management. The latter protects worst-case behavior from breaking machine learning consistency, while the former improves convergence time. And also, the communication manager has 2 objectives: communicate as many updates per second as possible without overusing the network, and 2, priorities more important model updates to improve machine learning progress per iteration. The first object is achieved by bandwidth-driven communication with great dignity, while the latter is achieved by choosing a proper prioritization strategy. In order to fully utilize the given bandwidth bucket, the communication manager permits communication of updates or updated parameters whenever the bucket becomes empty. The communication manager keeps track of the number of bytes sent last time to monitor the state of the bucket. In author's prototype implementation, the communication throws periodically querying the communication manager for opportunities to communicate. The size of each send is limited by the size of the bucket to control its burstedness. Bison spends a valuable bandwidth on communicating information that contributes the most to convergence. For example, gradient-based algorithms are interactive convergent procedures in which the fastest changing parameters are often the largest contributors to solution quantity. In this case, we prioritize communication of fast-changing parameters, which the largest magnitude changes going our first. When there is opportunity for communication due to spare bandwidth, the server or client communication throws pick a subset of parameter value or updates to send. The prioritization strategy determines which subset is picked at each communication event. By picking the right subset to send, the prioritization strategy alters the communication frequency of different parameters. Effectively allocating more network bandwidth to more important updates, it should be noted that the end of clock communication needs to send all up-to-date parameters or updates older than a certain clock number to ensure the consistency guarantees. Many data parallel machine learning applications use the SGD algorithm, which is sensitive to step size used. The current state of the art is adaptive reversion, which computes the step size for each model dimension and take into account both timelines and the magnitude of the update. The reversion differs from regular SGD in that it maintains an accumulated sum of historical gradients for each parameter. Gradient automatically updates the parameters and the accumulated sum. When a parameter is read out of the parameter store for computation, a snapshot of the accumulated sum is taken and returned along with the parameter value. A client will compute a gradient using that parameter and then apply it back to the parameter store. When this happens, the snapshots associated with the parameter is also supplied. The difference between the snapshot value and the latest parameter value indicates the timeliness of the update and is used to adjust the step size. The longer the updates are delayed, the smaller the step size, so that long delayed gradients don't jeopardize model quality. And the authors compare Bison LDA with the popular Yahoo LDA using the NY times and 10% of the QWeb dataset using 1 GB and 20 gigabyte in 20 gigabyte respectively. The figure shows that Yahoo LDA employs a parameter-server architecture that is similar to Bison's, but uses total acyclic parallelization. The compute throughput of Yahoo LDA process the same number of data points as Bison's. Each Yahoo LDA worker runs one synchronizing thread that iterates over the synchronizes or cached parameter in a predefined order. Where the author observed that Bison significantly outperformed The author observed that Bison significantly outperformed Yahoo LDA on the NY times dataset, but converged at the same rate on the QWeb 10% dataset. The authors also observed that as the clock tick size halves, the orange bandwidth usage over the first 2080 iterations doubles, but the average time per iteration doesn't change significantly. From this figure, where the author observed that the increased communication improves the algorithm performance, although simply turning clock tick size also improves. Algorithm behavior, it doesn't enjoy the benefit of prioritization. For example, MC640RM used only 63% of the bandwidth compared to BS8, but converged 28 faster. The difference is due to careful optimization, which cannot be achieved when application novel tunneling. Experiments with several machine learning applications on over 1,000 cores show that authors' technological significantly improve upon static communication schedules and demonstrate 2 to 3 times speed up relative to a well-implemented bound stateless system. However, their prototype implementation has certain limitations. While a production system should address those limitations, their evaluation nevertheless demonstrates the importance of managing network bandwidth. The author's implementation assumes all nodes have the same inbound and outbound bandwidth, and each node's inbound and outbound bandwidth is evenly shared among all nodes that it communicates with. Such assumptions is broken in a hierarchical network topologic typically seen in today's data centers, leading to underutilized network bandwidth. Although update magnitude serves as a good indicator of update importance for some applications, there are cases, such as when stored procedures are used, such as when stored procedures are used where it may be there may not be enough. For future research should look into exploiting more application-level knowledge and actively incorporating service feedback to client. Thank you for your watching.